In this video, we will talk about kinetic energy of rotation. We shall begin by relating angular and linear variables such as distance, velocity, and acceleration. Next, using the connection between linear velocity and angular velocity, we will introduce kinetic energy of a rotating body, or kinetic energy of rotation. We will then discuss moment of inertia for point masses, which comes naturally from kinetic energy of rotation. Finally, we will solve some problems to explain the concepts that we have presented. Let's start by relating linear and angular variables. We shall start with distance. Assume you have an object that is rotating about this axis of rotation that is coming out of the screen. It is rotating counterclockwise as shown. Let's assume at some point in time it travels from this point to that point, and in doing so covering an angular displacement of theta and an arc length of s. Now, what is the connection between the arc length s that is measured in meters and theta that is measured in radians? The arc length s is given as the radius of that circular motion times the angular displacement in radian. Now, it is essential to note that the angle here is expressed in the unit of radians and not degrees. The next pair of variables, the linear and angular variables that we want to relate, are the angular and linear velocities. The linear velocity that we are interested in here is the tangential velocity, labeled here as v sub t. So what is the connection between v sub t and the angular velocity omega, which in this case coming out of the plane of the screen? We can obtain the answer by differentiating that expression with respect to time. So ds dt equals r is a constant, d theta dt. So you see that ds dt is the linear velocity, that one, equals r, d theta dt is the angular velocity of this object for this rotational motion. The last pair of variables that we want to relate are the linear and angular acceleration. Now assume that this tangential velocity is increasing or decreasing with respect to time. So there must be a tangential acceleration as well. Now, how do we obtain that tangential acceleration, and how do we relate that to angular acceleration alpha that we have seen before? When we differentiate the velocity equation with respect to time, we get dv t dt equals r d omega dt. The left-hand side dvt dt is indeed your tangential acceleration, and d omega dt is the angular acceleration. So we can write the following, that to relate these two variables. Alpha t equals r alpha. So the subscript t again denotes the tangential direction of that acceleration. So to summarize, these three equations relate the linear and the angular variables respectively. Let's move on to kinetic energy of rotation. So as shown, you have a system with two masses, mass 1 and mass 2. Assume that these two masses are connected by this rod, a rigid rod, but a massless one. So mass 1 and mass 2 will rotate about this axis of rotation. Right here, the axis of rotation is coming out of the plane with some angular velocity omega. Note that since m1 and m2 is part of the same system and they are connected by a rigid rod, both will have the same angular velocity. However, the tangential velocity for m1 and m2 will be different. According to the discussion that we just had, the tangential velocity of m1, let's call it v1, is given by radius r1 times omega, and the tangential velocity of m2, let's call it v2, is given by r2 times omega. So what is the kinetic energy of rotation for the system? The kinetic energy of rotation is given by half, let's do the kinetic energy for mass 1 m1 v1 squared plus half m2 v2 squared. The sum of the two kinetic energies will be the kinetic energy of the system. Now if we can express v1 and v2 in terms of omega, the kinetic energy will simply becomes m1 omega squared r1 squared plus half m2 omega squared r2 squared, which can then be simplified as follows. So in this equation, we have factored out the half and omega squared because they're common factors, and you can see the terms in the bracket. The terms in the bracket can be labeled as I. So I is m1 r1 squared plus m2 r2 squared. And using that I, we can write the kinetic energy of the system in a following manner. So this I here is known as the moment of inertia or rotational inertia of the system, with an SI unit of kg meter squared. So this expression right here, half I omega squared, is the kinetic energy of rotation of a system. In short, for a rotating system, if we know what the moment of inertia is and what its angular velocity is, we can compute its kinetic energy of rotation. Just like for a linear system, if we know what a mass is and what its linear velocity is, we can compute the system's linear kinetic energy. So now the question is, what does moment of inertia or the rotational inertia represent? It can be viewed as a rotational analog of mass. Quite simply what it means is that the larger the moment of inertia of a system, the harder it would be to start rotating the system or to stop the system from rotating. Just like in the linear case, if you have two masses, one is 1 kg mass and the other one is a 2 kg mass, and if both masses are initially at rest, it would be harder to move the 2 kg mass than the 1 kg mass. Or equally, if let's say the two masses are moving with the same speed, 2 meters per second, it would be hard to stop the 2 kg mass than to stop the 1 kg mass. A point to note about moment of inertia is that unlike mass, which is constant and does not change, moment of inertia depends on where the mass is, namely the distance r from the axis of rotation. So if you have, let's say, an axis of rotation here and the mass there, and the distance is, let's say, r, the mass is m, so the moment of inertia is mass times the square of r. Now if you increase, let's say, the distance from the axis of rotation from r to 2r, now the moment of inertia will be different. It will be larger. It will be m times 2r squared. So in this sense, moment of inertia is fundamentally different from the mass of system. To highlight this point numerically, let's say you have a system consists of one mass, 1 kg mass right there. The distance from the axis of rotation is, let's say, 2 meters. Now the moment of inertia of the system about this axis of rotation equals to 1 times 2 squared. So you have 4 kg meter squared. Now let's assume I bring the 1 kg mass closer to the axis of rotation, now making the distance between the mass and the axis of rotation is 1 meter. The new moment of inertia of the system now equals to 1 times 1 squared, which is 1 kg meter squared. So you see how important the position of the mass is with respect to the axis of rotation. At this point, we would like to note that the equation for rotational kinetic energy, half moment of inertia, the square of angular speed, can be used to calculate kinetic energy of rotation for any bodies such as a sphere spinning like that, or a cylinder spinning like that, and so on. The only thing that we need to be careful about is the expression for the moment of inertia. The expression that we've written down earlier, namely mr squared, is for point masses only. If instead, let's say you have a cylinder whose axis of rotation is that line right there going through the middle of the cylinder, the moment of inertia for such a cylinder is given by half times the mass times the square of the radius of the cylinder, radius being this length right there. Or for a hollow sphere with axis of rotation going through the center, shown there with mass m and radius r, the moment of inertia for such a hollow sphere is given by 2/3 times mass times the square of the radius. Let's look at the following problem. So diagram below shows two particles, each with mass 0.6 kg. They are connected together and to a rotation axis at 0 by massless rods, so we don't have to worry about the contribution from these rods. They are massless. The distances from the axis of rotation are shown, 5 centimeters and 10 centimeters respectively. If the system rotates around the rotation axis with an angular speed of 0.4 radian per second, calculate the system's moment of inertia and kinetic energy. Moment of inertia, there are two contributions because there are two masses. The first contribution is the mass times the distance, 5 centimeters, 0.05 in meters, that is, plus another contribution, 0.6, and the distance is 10 centimeters, 0.1 meters. And you will get 7.5 times 10 to the power minus 3 kg meters squared. Having found moment of inertia, the kinetic energy of rotation is quite simply half times the moment of inertia that we have computed in part A times the square of the angular speed. So now that's going to be half 7.5 times 10 to the power minus 3 times the square of 0.4. And that will be 6 times 10 to the power minus 4 joules. And that solves the problem. Problem 2. A wheel will lose 400 joules of kinetic energy while its angular velocity decreases from 600 rev per minute to 450 rev per minute. What is the wheel's moment of inertia about the rotational axis, which is in the middle? So the initial kinetic energy of the wheel is given by half times the moment of inertia that we want to find times the angular speed squared. Angular speed is 600, unit is rev per minute, so we have to change to radian per second. So 1 rev is 2 pi radians, and 1 minute is 60 seconds. And do not forget to square it. And that will give you 1974 I in joules. Now likewise, the final kinetic energy is given by half times I, the moment of inertia that we want to determine, times 450 rev per minute. So 1 rev is 2 pi, and 1 minute is 60 seconds. And then you square that, and that's going to give you 1110 I joules. Since it will lose 400 joules, all we have to do is to equate that 400 to the difference, which is 1974 minus 1110 I, and you can solve for I, and that will give you I equals 0.463 kg meters squared, and that solves the problem. Thanks for watching.